Welcome to lecture 9 about virtual memory. Here you have the reading instructions, is chapter 3.3 to 3.6, and as always you have the pointers to other parts of the facultative book you can have a look at if you want to complement a bit the discussion. Sorry. So the objective here is to continue our discussion about memory management, going back from where we left, so paging, and describe the benefits of virtual memory. We will discuss concepts like demand paging, page replacement algorithms, and allocations of page frames. And then we will discuss what the working set model is, thrashing, and so on. These are a bit more advanced concepts, but hopefully it will be clear. Let's start with a rapid recap and the introduction. So the last thing we discussed last time was paging. We said we take a process, we divide the logical space into pages, then we take the physical memory, and that is divided into frames. The size of a frame and a page is the same. We even maintain stuff on disk organized into pages, so that when we load a process, we put pages into frames. And this is what I said, the page size is equal to the frame size. And of course, we need a page table so that we can translate the logical addresses to actual physical addresses. And as you can hopefully see now, since we have this disjoint way of maintaining the logical addresses or the logical space and the physical space with this intermediate thing that is the pages, frames, and how we translate addresses using the page table, we have less fragmentation. Paging doesn't have external fragmentation, it has only internal one, and that you can control better with the page size. Plus, again, as long as you have enough free frames, you can load a process independently of where the frames are, which is not true, for example, with contiguous allocation. We had better protection. This is since even the segmentation before paging we discussed. And it's also faster to load and swap processes. This we will discuss now. Because now, as you can imagine, it's enough to swap some pages rather than all the pages. But let's see this one step at a time. So the first question here we should think about is, what would happen if the operating system was sort of lying, let's say, and not really loading all the pages into the frames when you want to start a process? So I'm saying that it just does not load a specific page here, not that it places it in a different frame. Well, of course, the intuitive answer here would be, well, of course, it would be a problem, because when I access the page and I don't find it in a frame, then that, of course, it's a problem, which is, of course, a correct observation. But then you could think, but when would that be a problem? Because it is a problem only if you try to access page 3. As long as you don't access page 3, whether it is or not in the real physical memory doesn't really play any difference for the process that is run by the operating system. So if you want to oversimplify what virtual memory is, it's basically something like this. It's to use paging, but not to put everything really into the physical memory when you start the process, but rather put it there only when it looks like it's really needed. So basically waiting until the process says, I want a specific page, and then place the page in memory if it's not already there. A motivation behind this could be that, of course, a process is quite large. It contains a lot of routines and so on. And it's not that you are really running all these things at the same time all the time. This, we mentioned it a bit before, maybe in some discussion, if I remember correctly, and we will mention it now. Again, there is this concept of locality. So you start running a function. So for a certain period of time, you will be running that function. You will run instructions that are close by in memory because they belong to the same function. You will use the same variables many times in the same portion of memory and so on. So for a certain amount of time, you will stay there. Then you change function, you go to another place in memory where you are running other things. It's not that you use all the code all the time. So there might even be parts of the code that are not actually used during an execution. You can have unusual routines, you can have error codes, maybe there is no error, you don't need to run. So you can see that there is a reason why I don't really want to load everything, because it's not that you really need everything all the time. If you can load stuff only when it's needed, it can be, of course, an advantage. So first of all, you can run more processes than the ones you could run if you load all of them at the same time. So you are not really constrained any longer by the physical memory you have, okay? Each program takes less memory while running, so you can run more programs at the same time. It also takes less time to load a program, because you don't have to load all the pages, you just load some of them. So when you say start a process, the responsiveness gets better, because instead of loading, I don't know, 5 gigabytes of stuff, maybe you can run initially with a bunch of 100 megabytes and be more responsive. Now, of course, as always, trade-offs. What are the trade-offs in this case if you use this mechanism which places a page into a frame only when it's really needed? Well, of course, that you need a mechanism to check if the page is there or not. So the operating system needs a way to detect that the process is trying to access something that is not in memory and react rapidly. And here you will see it's again collaboration with the hardware. There will be a degradation in the performance accessing something that is in memory compared to trying to access something that is in memory. Finding out it's not there, waking up the operating system, letting the operating system react and go to the disk, fetch the page, place it where it should be, update the page table, and tell the process, okay, now you can access. Of course, takes a lot of time. You will pay this penalty. So the idea is that you should not pay this penalty too much, otherwise maybe it's not worth the benefits you have with virtual memory. And there will be more, but let's look at them later on.